Hello, I'm Nicholas Solomey, professor at Wichita State University, and today I'm going to be talking about my NIAC Phase 3 project, the construction of a CubeSat for testing a neutrino detector in space. This is in collaboration with other people here at Wichita State University, South Dakota State University, Marshall Space Flight Center, JPL, and the University of Minnesota. The project started with an idea. Can better or new science be done with dramatically increasing the neutrino flux by going closer to the sun? However, this technique needed a new way to detect neutrinos because in space, there's only the shielding you can take with you. And originally, this idea started with a NIAC Phase 1 study to answer these. The NIAC Phase 1 study conclusion was that if you went to 3 solar radii with a 10,000 kilogram detector, you would only need a kilogram or less. If the signal to noise would go up by a factor of 1,000 and the angular resolution would improve by a factor of 1,000. And we've also identified new science not able to be done with neutrinos on Earth that would open up a new frontier in heliophysics, astrophysics, and elementary particle physics. The NIAC Phase 1 project was the idea that the neutrino from the fusion reactions in the core of the sun would interact with gallium-69 or gallium-71, produce a conversion electron, as well as an excited state of germanium-61 or germanium-71. We were able to use simulations that showed the proper solar neutrino rate mixed in with the galactic cosmic ray rate and the galactic gamma ray rates, and we were able to look for this double delayed coincidence. And the double delayed coincidence was able to then be reconstructed as shown in these half-life plots. That was consistent with the expected half-lives of 2 microseconds or 20 milliseconds, depending upon which mode we were trying to reconstruct. This project then moved on to a NIAC Phase 2, and our study of the NIAC Phase 2 just concluded in the middle of September. It was the idea to improve the simulations of detectors and technology and the science that we did, build and test a prototype detector in the lab, and the first neutrino spacecraft mission analysis to the sun. There were some constraints that were imposed upon us, such as any first mission close to the sun would have to be modest at the level of a Explorer class spacecraft, which pretty much means less than $350 million in 5 years of operation. Here's a picture of the NIAC Phase 2 prototype detector on the right. And then it was encased and surrounded in a veto ray, which is shown on the left. It had a good energy resolution, less than 30% full width half max, had very good timing. The timing pulses of 20 nanoseconds for the conversion electron allowed plenty of time for the 2.5 microseconds to look for the first radioactive half-life decay. And we found exceptional rejection. Here's some plots of the energy resolution in the NIAC Phase 2 study. You can see this exceptional narrow gamma ray from a zinc 65 tagged X-ray detector, showing a good 30% full width half max. And we had very good, at the bottom plot, you see that depending upon the threshold we set in the liquid scintillator, the veto ray was 98% efficient at catching and rejecting these fake double timing pulses. So you combine all this and we have the implication for this double delayed coincidence as a way of tagging for solar neutrino interactions in a gallium enriched detector as very favorable. The simulations of the gallium neutrino detector involved the backgrounds such as galactic cosmic rays, shown here on the top plot, gamma rays shown on the bottom right plot, and neutrino interaction events shown on the bottom left plot. The detector simulation in space, the idea was to operate less than 20 solar radii reconstructed neutrino events equal to fake double pulse events. So you can see in this plot that, which is a plot of the distance the spacecraft is away from the sun, that when you're here at Earth, you're dealing mostly with cosmic backgrounds. As you get closer, the neutrinos from the sun increase, and at 7 solar radii, you have 80% of the events being recorded are that of neutrino interactions and 20% that of the cosmic interactions. And that allows for an exceptionally good science performance. So the mission study was a joint effort between Wichita State University Aerospace Department and Marshall Space Flight Center Advanced Concept Office. It involved all the scientists working on the project from Wichita State University, South Dakota, and Marshall Space Flight Center. It had to include a launch and 5 years of operation and demonstrate it can produce science. The development of the Solar Probe Plus spacecraft, now operating close to the sun, was actually $1.5 billion. And this amount would be very unacceptable for a first technology demonstrator mission. And we felt we could operate at the same distance from the sun as the Solar Probe Plus currently achieves as a demonstration that this detector in space would work. This is not that different than what the NASA Space Technology Mission Director did in the mid-1980s. In the mid-1980s, they designed, built, and in 1992 launched the Energetic Gamma Ray Telescope, called EGRET, the world's first gamma ray observatory. This produced a new window to the universe in high energy gamma rays and was followed later, 25 years later, by a major mission by the Space Science Mission Directorate, now called the Fermi Gamma Ray Observatory. And yet this spacecraft was the first time NASA or anybody operated a gamma ray detector above the Earth, and they opened up a whole new window on the universe as shown by this galactic plot on the bottom left. You could see the galactic core, you could see Crab Nebula, the Ganymede Nebula, and it was all being done in high energy gamma rays for the very first time. So we have the similar idea. Let's take this technology that was developed for Solar Probe Plus. If we copy it, we could save a huge amount of money. It will allow us to get close enough to the sun, such as Solar Probe Plus currently does, and operate it for science at a distance that is reasonable enough to do some new neutrino science and demonstrate that a neutrino detector can work close to the sun. We're going to just, in our design, copy the heat shield, the Solar Probe Plus, the solar panels and batteries, the solar radiators for cooling, and the communications. Our new part would be an electromagnetic shield, a 100-kilogram neutrino detector, and veto and shielding at the minimum level to save as much mass as possible. Here's a picture of the new components. You have this electromagnetic shield shown in red at the top. It's followed by 4 segmented neutrino detectors. We decided to do 4 detectors because we needed to get enough light to the end sensors, and we weren't able to do that across an entire 1.6 meters, but we were able to do it if we divided the space up among 4. All 4 of those detector modules were being encapsulated in a veto ray as well as shielding. And this is the new component that would then fly inside a spacecraft that uses some of the components very similar to Solar Probe Plus. The mission study was the launch from Earth, encounter Venus to help us modify the orbit, and every time we went around every other orbit, we would encounter Venus, and it would help us pull the spacecraft closer and closer to the sun. The idea of the least expensive launch vehicle we could find would be the Falcon Heavy to take us to Venus, and then the spacecraft would be on its own. The mission study itself involved the complete spacecraft, from system engineering and the detector components, instrumentations, radiation shielding, flight systems, power, batteries, avionics. And the idea would be we would like to collect in that at 7 solar radii that 300 fully reconstructed events, which would be equivalent to collect, and each event is equivalent to about 900 here on Earth. So our phase 3 is to build a CubeSat to prove operations of a double pulse delayed coincidence space with the veto shielding, measure fake double delayed coincidence rates in space, and measure spectrums. Here's a picture of our 3U CubeSat with the central detector and the avionics and the flight computer and some dedicated cards. Our mass has to be within 4 kilograms, and we would have no iron shielding because the CubeSat is uncontrolled orbiting the Earth, and so we have to replace the iron shielding with epoxy loaded with iron dust. So the history of the project starts in 2015. It involves several funding, such as starting off with a NASA F score, but a NIAC phase 1, NIAC phase 2. So far, NIAC has funded this project at 92%, and the launch and operations is not certain yet, but we are hoping that we could do this with other things such as the CubeSat launch initiative. And so we have a long ways to go. So thank you very much.